PCs, workstations, cars, and supercomputers now. So the Nvidia GPUs deliver unmatched visual computing with breathtaking interactive graphics that delight users and massively parallel computing power that accelerates work on the world's most challenging technical problems. So Jen-Hsun has been the recipient of the Morris Chang Exemplary Leadership Award for the Fabless Semiconductor Association. And prior to founding Nvidia, Jen-Hsun held engineering and marketing positions at LSI Logic, and he was a microprocessor designer at AMD. So he has degrees from Oregon State and Stanford. Jen-Hsun. Where'd he go? Welcome, Jen-Hsun.
Am I on?
You're on.
All right. Good morning. Good morning. It's great to see all of you guys. Many of you I haven't seen in quite a long time. We had some technical difficulties here. We could apparently we can go to the moon, but we can't cross the street yet. And so today I want to talk about the parallel computing era. And if you think about the various shows that we've been to at Hot Chips over the years, few, I think, are at the center of a discontinuous change in the computer industry as great as this one. If you think about where we are today, the computer is being driven towards parallel computing because of the demanding applications that people are dreaming up. And there are magical things that people want to do with a computer. On the other hand, it is being driven completely in the opposite direction for low power consumption. We would like to have teraflops of computing capability on the one hand, and only milliwatts of power consumption on the other hand. The milliwatts happening because we want computers that we could take with us with battery life for days and be able to use all the time and take advantage of what people are now increasingly called cloud computing or just web-based computing. And so the discontinuity is pretty significant, and it's very difficult to solve both problems at exactly the same time. You could have a whole conversation about mobile computing and low-power computing and some of the exciting things that are happening there. I'm not going to talk about that today. I want to talk about parallel computing. It's a huge task in itself and a huge space to talk about. So I want to talk about parallel computing. I want to call it GPU computing in the context of our conversation today. GPU computing because I want to make the case to you that it is most likely that the GPU will be the processor for parallel computing in the future. That on the backs of this particular device, on the backs of this particular product or product category, will likely to revolutionize computing altogether. You know, if I were to go back to 1993, and this is me and my first desk, and this was pre-PC on your desktop days. It was 1993, February 1993, and we started the company. And if I were to tell our venture capitalists that the reason why they should invest in Nvidia is because someday we will have a teraflops in one of our processors, and that processor will be used to play games as well as cure cancer, as well as stream video to millions of people on the web, and paint a vision so grand, I am sure we will not be funded. I am sure we will not be funded. We had much more modest dreams at the time. We just wanted to be a 3D graphics company, and we felt that visual computing on the computers of everyone would allow us to enjoy our computing experience as we could imagine it in our head. Well, 1 teraflops at the time, 1993, is miraculous on another level. It happens to be exactly the performance of the fastest supercomputer at the time, the thinking machine supercomputer. Now, I'm jumping a little bit too far ahead. Let me take you back to how we got there and why it is that today this dream is not only real, it is happening all over the world today. Our business, let me just put that in context a bit. You know, our business is organized into 4 different groups. We have 4 business units as we describe it inside the company. There's a consumer visualization business with a brand name called GeForce. This is This is the business that most people know NVIDIA to be about. You see it on our notebooks or desktop computers. People use it to play games and otherwise. There are hundreds of millions of GeForces around the world. At any given point in time, our estimate is that the active use is about 300 to 400 million GeForce processors around the world. We ship about 100 million more each year. We are also quite large in the professional visualization business. And in this particular case, people are using our processors to design content, whereas the GeForce business is about consumption of content, the enjoyment of content. We have created a new business called Tesla for high-performance computing. These are GPUs that have no display heads. These are GPUs or graphics processors that don't display anything at all. They sit in a cluster, they sit in a workstation, and people use it for general purpose parallel computing. And then our last business is really about mobile computing. Taking the computer technology that we know and love and reducing it, on the one hand, for parallel computing, to improve performance by several orders of magnitude. In the case of mobile computing, our objective is to reduce power by a few orders of magnitude. We believe that if you started from scratch with a blank sheet of paper, it is possible to design a modern, high-performance computer in just a few hundred milliwatts. And we have a product called Tegra, and I'd love to come and share that with you one of these days. Our business is, you see the results of our work all the time, and you could think of the work that we do as synthesizing reality, synthesizing worlds. But we also do a lot of interesting work in the area of augmented reality. This is one of my favorite areas of work. In fact, when you watch Monday Night Football and you see the yellow line or the blue line, the scrimmage line, that's rendered in 3D. Only in 3D is it possible for the football players to be standing on top of the blue line and yellow line, running over it while the grass is below it. You could also see us in the Olympics, sports events. In the case of Nastya Liukin's gold medal tumble, you saw her, literally multiple versions of her in one frame, so that you could see her and her athletic abilities literally in a single shot. You could also see us rendering the flags on the bottom of the ice as the ice skaters run through. And then also recently, 3D Graphics was able to create a virtual set for Ann Curry for the Obama elections. And so you could see that 3D Graphics is not only used to create and for people to enjoy video games, but 3D Graphics has a wonderful capability of augmenting reality as we know it. This is an area of great interest to us. I think this is one of the most important areas of innovation going forward, and I'll show you some examples of that later on. Now, from a technology perspective, the GPU has evolved probably faster than any technology component that we know. The first product that we designed was not the Riva 128 that I showed here. It was actually a chip called the NV1. And as with every startup, the first product should be a disaster, and in ours was a disaster of disastrous proportions. It was a chip called NV1, and people who know NVIDIA have marveled at how the same team could have built Riva 128, but have built NV1 just a few years before that. I marvel at it myself. But you know, that's how it is when you're a startup. So we had built a chip called NV1. It was a commercial disaster. And we had built a chip called NV2. We canceled it before it became a commercial disaster. And then we built a chip called NV3, which is Riva 128, and it was a commercial success. Riva 128 at the time was the most complex non-CPU ever built. It was the most complex non-CPU ever built. And a lot of people said, there is no way you could sell this chip. And I remember going to PC OEMs, and they would tell me, first of all, nobody needs 3D graphics. Second of all, nobody plays games. And third of all, this chip is way too expensive. We know a VGA controller goes for a price of $7. And I told them, but the cost of Riva 128 was $28. They said, well, the price is $7. And so I built it anyways. And we built a whole bunch of them. Riva 128 was an allocation its entire life until we replaced it with the next generation called Riva TNT, which had a cost of $48, and it was in allocation its entire life. And so we discovered this rhythm and created a whole bunch of very exciting processors since. GeForce 256 was the first graphics chip that we coined the word GPU and invented this whole new product category called a GPU. Shortly after that, we introduced the Pixel and the Vertex shader with a GPU called GeForce 3. And that was in our early 2000s. And with the Pixel shader, and making the graphics chip programmable, a little bit programmable, it's modestly programmable. Making it modestly programmable, we opened up the whole space of computer graphics to not just acceleration, but artistic expression, making it possible for artists to describe their imagination in different ways, depending on the way the programs are written. We shortly after that came out with an innovation that was very important to us, and I think that it, in fact, put us on this trajectory of a parallel processor forever. And that innovation was called CG, C for graphics. CG was really about a shading language, a way of describing programmable shaders in a high-level construct that is compilable. CG, shortly after that, inspired HLSL and GLSL, the two important shading languages now available for Windows as well as OpenGL. All three shading languages are available to the world today, and we support all three enthusiastically. And then after that, we discovered that people wanted more and more programmability. And I'll show you the results of that in a moment, but that was when we invented an idea called CUDA, making the GPU completely programmable. We realized that people would love to use the programmability of the GPU, but would like not to express their problems in triangles and texture maps, but to be able to express their problems in a high-level computing language like C or C++, and make it more accessible to people. And so that is the roadmap that we've seen. In this particular roadmap, I didn't include our latest generation, but it includes up to basically about 2 or 3 years ago. In the course of that 15 years, we've improved or increased the complexity of GPUs from a few million transistors to over 1 billion transistors, almost 1,000 times in complexity. I think very, very few semiconductor devices or processing devices has gone through that rate of evolution, that rate of innovation in such short a period of time. Now, the important thing about that particular comment has to do with the fact that if the industry wanted to find a medium by which, a platform by which there is enough R&D investment necessary to advance the computer industry, you could either do it on the backs of the CPU or you can do it on the backs of the GPU. Both of them support billions of dollars of R&D budget. Both of them have miraculous processors and have the volume necessary to take a new architecture into the world. And that's the reason why we thought that it was possible, that we felt that it was possible for us to invent a parallel computing, a general parallel computing architecture, and introduce it to the world on the backs of a chip that had a day job. And the day job was playing games. And so we invented CUDA and brought it to the world. There's now about 100 million GPUs in the world that are CUDA compatible. You write the application once, and it runs on all of these 100 million PCs with CUDA GPUs in it. Now, along the way, we dramatically changed the way computer graphics looks. In 1993, when we first started, computer graphics was basically about texture mapping, and the company that was going to be successful was the company that was able to figure out a way to do inverse texture mapping with Z buffering on at a fill rate able to sustain about 60 hertz, 30 to 60 hertz. It was a battle of fill rates. The problem was relatively simple, if you will. The amount of mathematics was increasing all the time, and it was a battle of execution, if you will. And so that was the age of the 3D graphics accelerator. The graphics accelerators of the time were completely fixed function and an enormous pipeline, an OpenGL pipeline, if you will. When we introduced the idea of the programmable shader, it became pipelines of processors. No longer just fixed pipelines, but pipelines of processors. And these programmable shaders allows, as I mentioned earlier, game developers to express their artistic imagination in very different ways. And that's the reason why we felt that it was possible for the video game industry to continue to expand as different games had a different look and feel to it. That a game wasn't just about fun, that's a very important part of it, and arguably the most important part, but it also had to be beautiful. No different than a movie had to be a good story, but also has to be an exquisite work of art. And so programmable shading made it possible for game developers and artists to express themselves artistically. But we wanted to go even further. And we wanted to take programmable shading to the next level. And we called that computational visualization. Computational visualization is no different in concept than computational chemistry, computational biology, computational astrophysics. We want to not only be able to articulate the surfaces using high-level shading programs, but we want to be able to articulate and express the entire graphics algorithms in computer software. Now, just to give you a demonstration of how far computer graphics has come, we're going to show you the world's first interactive ray tracer. And so why don't we switch over. This is Phil Miller driving, and hang on. Oh, so what you just saw initially looks like a photograph, but it's not. It's a rendered scene. This entire scene, the Bugatti is 2 million polygons. This entire scene is ray traced with global illumination. You could see that the multiple bounces of light is lighting up illuminating the car in slightly different ways, so that the colors of the environment is actually shining on the car. You see, so obviously ray tracing allows you to ray trace starting from the eye view, but also generates rays as it hits the glass for refraction and reflection. We're using full global illumination, and notice the soft shadows. Everything here is being generated in real time, so there are no pre-baking of the data structures. Creating the data structure for beam traversal is one of the most complicated part, or the performance degrading part of ray tracing. All of that is being done in real time. And so Phil, as you see, is changing the lights. He changes the car. He could open the doors. And maybe what we'll do is we'll ask him to go inside and do a really macho ray tracing move. Because once he goes inside, all of the light is indirect. Okay, so it's no longer, so as soon as he goes inside, he's relying on global illumination to now light the inside of the car. Otherwise, it would be completely dark. And you notice that as he's interacting with the car, he's moving probably at around 5, 10, 15 frames a second. But when he settles down, the ray tracer goes to work, and within about 10, 15 seconds, you see a rather good car, and then within 5 minutes, you have the final film rendered image. Ray tracing still has a long time to go, but you could see this. By the way, this is running on 3 G-forces, 3 GPUs, and each one with almost a teraflops. So it takes about, in this particular scene, about 2.7 teraflops to be able to sustain the performance that we're looking at here. And as you can see, this is almost photorealistic. Okay, so the benefits, thank you very much, Phil. So that's the benefits of, there we go, thank you. One of the best parts of our jobs is the eye candy that comes with building these things. It costs us about $1 billion to build a generation of GPUs. The first graphics chip, Riva 128, took about 12 engineers or so, working 24 hours a day for about 9 months. And that's the nature of a startup. A next generation GPU would take something along the lines of a few thousand man years. It takes about 3 to 4 years, starting with the architecting of the processor, then to the design and implementation, and that takes about 2 to 3 years. And so now these GPUs sustain about $1 billion in R&D, and thousands and thousands of man years later, and the thing that generation after generation, we just can't wait to get back into the lab so that we could see what it could do. And so this is one of the best things about our job. Okay, so revolutionizing computer graphics. We've really come a long ways. And so now what I want to do is I want to take this computer graphics problem, and I'll take a very simple version of it to illustrate why it is that the GPU has become such a wonderful parallel processor. Now, if I were to just take a snippet, if you take a look at that green bar, that basically half of it represents 1 frame time. And what I show in the blue are things that are very difficult to parallelize, or maybe it's the critical path of a particular piece of code, and the green part is all rendering. And the rendering has a lot of different components. It has obviously all of the transforms and the setups and the rasterization. You have texturing, you have all of the work that we have to do on the back end with Z buffering and blending and such. I'm excluding all of that because it's just complicated to add. It turns out that the vast majority of all of the operations in a graphics chip in a GPU happens to be the things that I'm excluding. But if I just focused on the simple things to add, the pixels that you see and the shading that you do on it, okay, that represents about half a teraflops in today's games. And so let me do the simple math for you. It's a high definition resolution, so 1920 by 1200 or 2.3 million pixels. And let me just estimate a depth complexity of 3. And we say that each component, RGB alpha, has about 100 shader instructions to it. Just now, when you look at the ray tracing demo, that particular one, I'm going to guess is probably somewhere along the lines of 1,500 or 2,000 instructions per component. And it was all done in high dynamic range, HDR lighting. But let me just use this particular example, 100 shader instructions per component, 4 components per pixel. And on average, sometimes they do a multiply add, sometimes it's just an operation. And so 1.5 flops per instruction on average, 60 frames. And suppose we were showing you the outside stereo graphics, multiply that by 2. So that basically adds up to about 500 shader gigaflops. Now that represents about 10% of the total math or computational capability inside a GPU. The rest of it, a GT200, which is what you're looking at outside, has about 6.4 tops. Okay, so 6.4 tops. That's the amount of math that we have to do per frame. Now, by doing it that quickly, 6.4 tops, we could achieve 30 frames per second, which is what you're looking at out there, or 60 frames per second or so. Now, if you were to take the theoretical limit, the peak performance of a great CPU today, designed for a very different type of problem, whereas the computer graphics problem is data parallel by nature, the CPU was designed for something that was task parallel by nature, has a very different behavior and different constraints. But if we just did the simple math, 3 gigahertz and 4 cores, 4-way SIMD, 2 flops per cycle, that gives you almost 100 gigaflops, which is fabulous. Fabulous for general purpose computing. Okay? So 100 gigaflops, if you were to compare that to about 5 tops, right? And if you were to say that a CPU is going to have more cache misses because the data is so large, and let's say that they're waiting about half of the time, you're basically 100 times away. You're 100 times short of being able to run an application in real time. And that's the reason why the GPU was invented. Now, we could improve the performance by whatever the percentage is every single year, but the fact of the matter is, improving performance by 20, 30, 40% each year, it'll take forever to get to real time. And so we invented an architecture called a GPU to do that. Now, going forward, there are other challenges of scaling, using brute force, of scaling these processors. And one of the, I'm sure many of you have read this, if not all of you have read this, the paper written by Patterson and the team up at Berkeley recently, and they talked about the limitations of the instruction parallel processor as we continue to scale. The performance comes primarily from frequency over the years. And yet, as we continue to increase drive strength, it comes at the expense of power. And now, the incremental benefits of drive strength comes with it the disbenefits of more power than the drive strength it derives. So power is becoming increasingly challenging. They talk about how transistors are free, but power is not. Then there's the memory wall. Math is free, as we've shown you. The math of a GPU, 6.4 tops in a GT200 is effectively free. 6.4 tops. But memory access is not. Load store is not. And going forward, bandwidth or computational bandwidth would continue to scale at the square of latency. And so latency is increasingly a problem. And then lastly, of course, the instruction level parallelism that so many of us have worked on over the years. We're just running out of ideas. Out of order execution is a wonderful idea. Branch prediction is a wonderful idea. VLIW is a wonderful idea. There are so many ideas, but there's just so much instruction parallelism to discover. And so he calls these three walls, among a few others, together to be the brick wall. Now, we're going to approach the problem a little bit differently. We conceptualize that there are two types of problems that a program is running. There's the task parallel part of it, which is highly sequential. There's whether it's state machines, a combinatorial logic, decision making, and whatnot. There's also data parallel parts of the program that are in fact easily parallelizable. People have described 3D graphics as embarrassingly parallel. And so we think that the world needs to have this co-processing idea where one processor is designed to be task parallel and another processor is designed to be data parallel. One processor is rather latency intolerant. The transistors are very fast, whereas the other processor is latency tolerant. Instead of using caches, we use enormous number of threads. Instead of a few very fast processors, we use hundreds, if not thousands, in the future of slower processors. And so these two different design techniques are rather different. And by using these two different design techniques together, if we could create a programming architecture that works, and we call it at Nvidia CUDA, we could speed up applications dramatically. And in fact, we do. And so this architecture we call CUDA has these characteristics. Hundreds and if not thousands of processors, they're latency intolerant, they execute thousands of threads per processor. If it's waiting for a memory reference, it just goes to another thread and start working on that. If it's waiting for another memory reference, it just goes to another thread and works on that. And so it's never really waiting for anything. The throughput in aggregate is very high. For any piece of code, the predictability of it is rather low. But that's what the CPU is good for. We've added a few things to CUDA over that of a 3D graphics processor to enhance its ability to be general purpose. For example, load stores and on-chip shared memories so that all of these processors could collaborate and share data among each other. And then we created an architecture that allows us to scale it over all of these GPUs. This is something that's really fabulous. You write the application one time, and the architecture figures out how many processors available, and the performance that you get is literally a scaling of that. Now, this seems magical from parallel computing perspective, but for a video gamer, This is perfectly obvious. Every single generation, a video gamer would buy a new GPU, put it into their PC, runs the same application, it just runs twice as fast. And so for a video gamer, this notion that you write once and scale arbitrarily, depending on the number of processors you have in the system, is rather obvious. And so these are the characteristics of CUDA. Now, using that characteristic, if I were to speed up an application, and based on the simple math that I was doing earlier, 100 times, and if we postulate that the vast majority of the application is parallelizable, notice the speed up could be quite dramatic. And in fact, we experienced this speed up. And not only that, most of this code could be parallelizable in the sense that it could even be overlapped. And so no longer is the critical path necessarily even blocking the speed up. You could overlap the sequential part with the parallel part. Now, to illustrate this, I just took 2 random games that just came out. This is Fallout 3 is in one column, Far Cry 2 is in the other column. And to show you how well overlapped these codes are and how well tuned it is for parallel computing, notice in the one case, Core i5 with a GeForce GTX 275. The 275 is basically your $179 retail graphics card. Okay, so this is the sweet spot of the video gamer. And running that at high definition, 4xAA, in the case of Fallout 3, you get 69.1 frames per second using Core i5, and you get 69.8 frames per second using Core i7. The 2 applications, or the 2 configurations, the GPU is now the critical path. It's completely overlapped with the sequential code that the CPU is running. Far Cry 2, same behavior. Okay, so it is possible to gain substantial speed up and in fact have it be completely overlapped so that the 2 processors don't wait on each other. Now going forward, where do we take computer graphics? We can make things more and more beautiful, and that's certainly one of our objectives, to make things more and more beautiful. But we also want to make the world dynamic. Instead of using artists to draw your clouds and your smoke and your fire, we would like to simulate everything. Instead of using artists to simulate the waves, we would like to to draw the waves, we would like to simulate everything. And so to show you some of that, let me give you an example. So this is, for those of you who have seen Harry Potter, the ending scene is extremely difficult to do. This is where Dumbledore shoots flames out of his hands, and the flame is directional, okay? And so he could actually direct where the flame is going to go. Now, most of the time in movies, you've seen that the flames are actually sprites of real flames. But sprites of real flames difficult to direct. And what they wanted to do is they wanted to synthesize and simulate the flame in such a way that it literally looks like something that Dumbledore is controlling. Now, fire is amazingly complicated because every single frame, every single part of that fire is different. It's alive, it's moving, it's dynamic, it's turbulent. And so simulating fire is incredibly hard to do. The folks at ILM created a fire simulator that runs on top of CUDA. So let me show that to you now. So this is fire simulation running on CUDA. It still takes hours to do this. Instead of days, it takes hours to render the entire scene. But as you can see, it's not only realistic looking, it is also beautiful. The next level of computer graphics is really going to be about simulation of the world, because there's just things in the world in the real world, that are just impossible for artists to contrive and draw in a way that would be as beautiful or as stunning. Okay, so the industrial light and magic fire. If you guys are interested, there's a paper written about it at SIGGRAPH just recently. Okay, let's go to the next slide. Can I come back? And so this co-processing, we talk about co-processing, we argue that in fact you need co-processors, that you don't want just a GPU doing all of the work. And the reason for that is because every so often you're going to run into state machines and control code and combinatorial logic that is in fact very, very difficult for the CPU's latency tolerant processors to do well on. So on those code, we could end up being 100 times, 200 times slower. And so you want the CPU and the GPU to coexist. And as we look at a large space of applications, whether it's traditional computer graphics, okay, or ray tracing, there's a large amount of software, there's a large amount of code that is either serial in nature or modestly parallel or modestly serial, however you want to think about it, and vastly parallel. And the degree by which there's code in each one of these territories or these type of domains change and differ from application to application. But we see that the vast majority of interesting applications fall in this space. So ray tracing, you have to create the acceleration structure by which you trace the ray. You traverse that structure. Neither one of those are extremely parallelizable. They're modestly parallelizable. But shading and tone mapping and such are extremely parallelizable. We see the same thing with physics. Collision detection has a large component of parallel code in it. Certainly smooth particle hydrodynamics, which is simulating fluids using particles. And I think we do have some examples of that. This one isn't using SPH, this is using FFT. But this is 3 512 by 512 FFTs, and the height fields are being blended with Perlin noise that's generated on the GPU. The entire scene is rendered. Once the math is done, the GPU then switches mode from CUDA to DirectX or from CUDA to OpenGL to render the scene. And this is all rendered with high dynamic range. This particular application, I believe, is running on OpenCL. Okay. And so let me show you another one for physics. So this is simulation of water. So why draw water when you can simulate it and have it be so beautiful? This particular wave, water demonstration, takes about 2 milliseconds on a GeForce GTX 275 compared to the frame time that you have of 16. Okay. Here we're doing a 3D Navier-Stokes fluid simulation, 3D fluid solver. And Tony, you said there was 128,000 particles or 262,000 particles or so. So we're using the solver to generate the fluid motion. But on top of that, we have to, for each one of the particles, we're doing a volume rendering for the shadows, as well as motion blur. Okay, all of this is being done in real time. Now, this is a contrived demo trying to show you where particles are, but obviously in the future, smokes from fires will become completely interactive because they're all particle systems. So when you walk through the fire or walk through the smoke, you'll see how the smoke will interact with the environment. Much more realistic, much more beautiful. Thank you, Tony. And so there's simulation of nature. That's extremely, that's the next level. And we think that that's incredibly exciting. And you're starting to see the simulation, physics simulation being used in film all over the place. So whether it's Harry Potter with the directional fire, directable fire, or that scene in Star Trek where the Enterprise came out of warp behind the moon of Saturn and floats up above the clouds, and the cloud breaks over the hull of the USS Enterprise. That's beautiful. Or when the balloons were set free in the movie Up, and the balloons are all interacting with each other, lifting up. That's really, really hard to render and to have an animator do. And so movie or Transformer 2, where they're destroying the pyramids, that is all simulated with physics simulation as well. And so you could see that movies are moving in this direction. We would like to take video games in this direction as well. Now, there's also some things that are simply not possible to pre-animate. And the reason for that is because you don't know how it's going to interact with the world. Here's a really innovative company called Natural Motions, and they're using a physics engine that runs on top of CUDA. It's called PhysX. And what they're doing here is they're combining and morphing motion capture so that it's convincing, but when you're tackled and when it runs into other characters, the rest of that is simulated with physics. So why don't we show them that, Tony? Okay, so all of this, if you look at, here we go, that is all physics simulation. That's physics simulation. You don't know that you're going to get hit like that. And so how would you motion capture that? That would be really painful to mocap. You would have, here, I want you to get nailed in the back. And so each one of these sequences has elements of motion capture, but the rest of it has to be simulated. And so this company called Natural Motions is doing just some fabulous work in this particular area. So again, physics simulation, because it's just not possible to do it in art. Thank you. Is it mine? Now, we started down this path of co-processing, shifting the architecture of the computer from central processing with accelerators to co-processing on two general purpose processors, one being the GPU and one being the CPU. And our purpose, of course, immediately close to our application, are computational visualization and physics simulation for world simulation. But that same general purpose architecture could be used for all kinds of interesting applications. You could use it for molecular dynamics. Each one of the molecules are simulated as a particle with force fields being applied to it. These force fields are applied to it based on the location of that particular molecule and the surroundings, the surrounding molecules. After all of that is computed, Newton's equation is applied to simulate the direction of it. We have a nanomolecular dynamic simulation outside running in stereo, and so it's worthwhile to take a look at that. The speed up that we're getting from this particular example is just extraordinary, and we're seeing that level of speed up all over the world. Ever since we've set CUDA free, and people realize that the CUDA GPU is available from every single computer company in the world, big or small. Every single computer company in the world offers a parallel computer, and all you have to do is download a CUDA SDK, and you're instantaneously, on your laptop or desktop, you have a supercomputer. And so this phenomenon is spreading all over the world. We're seeing the adoption of CUDA and GPU computing just literally through every single corner of the world. It's being taught in universities now. CUDA is the most accessible parallel computing architecture to students, and so people are using it for education, computer science curriculums. I think it's being taught in over 100 universities around the world now. We have almost 1,000 clusters implemented with GPU computing around the world, whether it's governments, oil and gas companies, biotech companies, a lot of universities. And the number of applications that are showing up, that are cropping up, is just growing organically. Here's some really interesting examples. Quantum chemistry is too hard for me to grok. Lattice Boltzmann, Euler solvers, GROMACS, and molecular dynamics application. And you're seeing speedups that are really quite astounding. 130 times speed up. Well, it's absolutely possible when the application is 99.9% or 99% parallelizable. And so we're seeing speed ups all over the place. Now, this isn't speed up of 25%. This is a speed up of 30 times. 30 times speed up. This is when we see speed up like this, for us, it seems rather obvious. When some people see speed ups like this, they think it's outrageous. But it's not. It's perfectly obvious if you think about it from the standpoint of the amount of parallelizable code that is in an application. Now, here I'm just using this is Amdahl's law, calculation of speed up, and I'm using on the horizontal axis 1x, and then you have 4 cores, and then you have 1 core plus a GPU. And the GPU, I postulated here 50 times the peak performance. Okay? Not assuming efficiency differences between a latency intolerant processor, but just doing the simple math. And you could see that in order for you to get speed ups of the 20 times, 40, 30, 50 times, 100 times, your code has to be nearly completely parallelizable. And in fact, we're finding applications like this everywhere. Computational photography is this way. Image processing of all classes are this way. Okay, so a lot of interesting applications that are up in the parallelizable realm of some 99% or 98%. Now we're seeing these installations, as I've told you, all over the world, and I just wanted to highlight one thing. This one particular installation is at Hess, and they're using it for seismic processing. Seismic processing is kind of interesting. It's an inverse analysis. Instead of starting with a model and then trying to figure out how the model behaves, they start with a seismic source, like dynamite, and they monitor the reverberations or the reflections from that seismic source. And depending, whenever the shock waves pass materials of different density, what they call impedance, it would reflect back at certain level of magnitude and velocity. And so they collect all this information and they try to reverse engineer, if you will, reverse the terrain that is being analyzed. The amount of computation that the oil industry does is really magnificent. And one of the things that I learned as we started to work with the oil industry is the valuation of their companies is not based on the financial results today or tomorrow. It's based on the amount of reserves they have. And so they're all in a panic to figure out how much reserves they have because it directly relates to the valuation of the companies. And so this is an area that they put an enormous amount of research in. Well, we have many clusters now installed all over the world, and we have clusters installed all over the United States, in the Middle East, and China. And these clusters are showing amazing results. And the thing that is obvious to all of us is that when you have speedups of this extraordinary capability, suppose you were able to achieve a speedup of 50 times, and you added a processor of equal power dissipation, your perf per watt is really magnificent. You reduce cost, you reduce power, you reduce space. And so most of the server rooms that we're working with these days, the challenge isn't just the amount of computation they could afford. The challenge for them is the amount of power they could deliver and the physical space that they have. So many examples like this. What some people call heterogeneous computing, what I just call GPU computing, has extraordinary benefits. Now, if I were to map this forward a few years, and we said that a CPU alone is improving at 20% per year right now, and whether it's 20 or 30% or 40%, it doesn't really, in the final analysis, matter. Over the course of the next 6 years, by 2015, you'll have 3x, 4x, 5x, 6x improvement in performance. That's certainly not bad, and I would certainly take it, and we'll count on it. We'll certainly bank it. But if you were to use a heterogeneous architecture, a co-processing architecture like a CPU and a GPU together, you get a speed up, and here I simply used a speed up of 50, and because we're using an architecture that is latency tolerant because we're using more transistors than fast transistors. This architecture is more likely to scale with time. And so if I were to just to map those two numbers out, you get 570 times improvement in performance over just the CPU alone over the course of the next 6 years by 2015. And that's what everybody's seeing. What the oil and gas companies are seeing, what researchers around the world are seeing, what biochemists are seeing, is that they have an opportunity for the first time to accelerate computing by a few hundred times, many orders of magnitude, for the first time in a very long time. When I was in Japan recently and I was giving a lecture, one of the professors came up to me and he said, this is the second, and this old man that does computational fluid dynamics his entire life, and he was doing plasma simulations. And he said, there's 2 times in my career where I've had pleasant surprises that I believe will change my life. And the first one was the Cray-1. And this was his second. That a student told him to run down to Akihabara to buy a graphics card used for playing video games, to download a CUDA SDK, and he would have a supercomputer on his hands. Well, in Japan, he now teaches courses, he writes books on CUDA. He wants to share the idea with everybody. And so we have just CUDA and parallel computing, or GPU computing, is clearly the greatest contribution we've ever made to the computer industry. Now, looking forward, they asked me, some of the ideas that I have about the future. Well, one idea is that we have to figure out a way to innovate not just on semiconductor process, but architecture and software programming tools. They asked me, what are some of the things that you could imagine doing with this? I don't know if what I want to share with you is visions of the future, but I can surely share with you some of the things that I love the most. The things that I love the most, I love the fact that we're going to have a universal translator. With enough computational resources, we'll be able to talk to each other over a video conferencing system. You'll talk to me in English and I'll talk back to you in Chinese. Or, and of course you'll hear it in English and I'll hear Chinese. So that's the hope. And all of this could be done in real time. The idea of a universal translator, I believe, is just around the corner. One of my favorite things is augmented reality, and you can start to see augmented reality applied itself in very mundane and very normal usages of mobile computing. This is an application by a really clever company in Europe called Layar, L-A-Y-A-R. And it literally will tell you what hotel you're looking at. You press a button and it rings the hotel. It'll show you what restaurant you're looking at, and it pops up the menu, and you could call it, to make a reservation. The number of applications of augmented reality in the form of mobile computing is pretty fabulous. I'm going to leave you with one demo, and this is one of my favorite pieces of work by a company in Europe called RTT. They use our GPUs for both the computer vision side as well as the rendering side. And so this is obviously recognizing that tire, but what you see in the screen is rendered in real time. And look, it's photorealistic, and it gets better. I just love this part. Their engineers are so clever. So it's a photorealistic rendering of the rim, and now he's lighting it. Obviously, the rim is not in real life, but the light is. So augmented reality. I started with some examples of how augmented reality is changing the way we enjoy television. Augmented reality will change the way we enjoy mobile computing, find places, find people. Instead of typing in a Ferrari and then for images to show up on Google, you'll hold up your cell phone and it will tell you that this is a new Ferrari, the Ferrari F459 or 458 or whatever, and it will do it in reverse. And so these type of capabilities are certainly just around the corner. At this point, let me open it up for some questions. I enjoy the opportunity to speak to you. I think that this is clearly one of the most important times in the computer industry that I remember. And not only are we making processors faster and faster, but we're creating new architectures that will speed up applications many orders of magnitude. Thank you. Can I take a couple of questions? We have about 5 minutes. Yes, sir.
Hi, Dave Patterson from Berkeley.
Hey, Dave. How's it going? How are you?
Thanks.
I think, hey, guys, everybody, give him a round of applause. You know,
I'll ask a question after every talk.
Where would we all be if it wasn't because of your textbooks?
Oh, all right. I withdraw my question. No, let's see.
It's okay.
I think the question.
You could take credit for all of this.
I think a question for a lot of architects. I mean, the data level parallelism and what you're able to do is really, inspiring. I think the kind of question for the architects, and obviously this has something to do with business, is a separate chip for the CPU and a separate chip for the GPU. You know, if you were to start today and there were no business constraints, you'd probably put them closer together. And I guess kind of the question is, clearly there's a bunch of apps that have the data level parallelism with the split that work great.
Yeah.
Kind of how do you, leaving the business part aside, how do you see what that split's going to limit what we're going to able to do?
Yeah, that's a really good question. And I like the fact that you started that question with the context of business into it, because obviously all of this innovation couldn't be made possible if you didn't have $1 billion R&D.
Right.
You wouldn't have $1 billion R&D if you didn't have a business. And so they kind of go hand in hand. I see that the architecture is split up into 3 different planes. When we look at computer architecture, we look at it from the programmer's view. That's one view of the architecture. There is the PC company's view. Dell's never written a program ever. And so they don't really care about the programmer's view so long as there are killer apps. And their view is a product architecture view, the motherboard architecture view, what connects to what chip, and how best to procure those devices. And the third one has to do with the chip architecture view. It could be designed as 2, it could be designed as 1. They both have benefits. The benefit of designing as separately in the beginning, as most of the ideas in the computer industry have shown up, by designing it separately on a separate chip, we could innovate on that chip without risking the entire architecture. And so in the case of CUDA, we built it on the backs of a processor that most resembles a parallel processor, as a beginning to bring the idea to the world. Now that the world recognizes this as an opportunity to go forward on, I think that you're going to see a lot of different implementations. You'll see discrete implementations because there are some people who just can't get enough performance on the data parallel side. And we see a whole bunch of those kind of people. You're going to see some implementations where the CPU and the GPU are unified. The challenge for which is interesting. Most of the upcoming CPU, GPUs unified have integrated graphics, but no parallel computing. And so then you have to wait another 4 or 5 years for that processor to show up. So you could see that we can bring innovation to the marketplace a lot more quickly if they were separate. But you're going to see all 3. You're going to see architectures that programmers will have to get used to, unified architectures as well as separate architectures. Programmers, PC OEMs will buy unified chips as well as separate chips so that they can have workstation SKUs and laptop SKUs. And then, of course, chip designers will have to learn how to design products that are based on these different constraints. That's kind of the reason why the PC industry, for all of our time in it, We've predicted that the graphics chip would get integrated into the CPU now for about 10 years, maybe a little longer, about 15 years. Since the beginning of NVIDIA, people thought that the graphics chip would be integrated into the CPU. But every year, something new comes along, and it's so important to have it that it continues to be separate. This is an interesting statistic. The PC industry has about 300 million PCs. And integrated
per year,
graphics per year.
Yeah.
Yeah. And integrated graphics represents about 60%. But discrete graphics represents about 60%. That math doesn't work, with the exception of the fact that a lot of integrated graphics has a discrete graphics next to it. And so I think that it's a matter of combining architecture, science, and product design, and finding a space that allows us to move the industry forward while considering all of those factors. That's you know, you ask a very good question. Those are the dilemmas of architects and business people and product design people.
All right, thanks.
Yeah, thanks, Dave.
Hi, so you mentioned writing code for either a CPU or a GPU. Do you ever see a time when you're actually, one is helping the other, so you're offloading a task that was written for the CPU, let's say, and getting some help from your GPU and returning that result back? Or do you see them always being in separate paradigms?
In fact, the first case that you described is the vast majority. The data starts out in system memory at some point, and so that data is copied over to our GPU. You know, the benefit of that frame buffer, as it turns out, even though there's a separate copy, that frame buffer is so fast. It's many, many, many times faster than system memory, as you know. And so that frame buffer has the benefit of being essentially an enormous cache. There's that initial copy. Then, of course, we do our parallel processing on it, and at some point, we might have to copy the data back. That copy is asynchronous, so that the main code doesn't have to, the CPU doesn't have to stall waiting for that code. But still, there's that copy. One of these days, we might be able to design and work through some of the challenges that Dave and I were just talking about, whether it's architecture, product design, as well as economics of business. Define a architecture where you can do a little bit less of that copy without compromising the bandwidth that we so dearly love.
Thanks.
Yeah. Yeah, Willie.
My name is Willie Lu. I'm running my first generation mobile R&D, both in Palo Alto and China. One question I'm very interested is, I'm right now designing the next generation 4G, first generation, the smartphone architecture. I'm the architect. So I agree with you that the CPU plus GPU for the smartphone, also the mobile application, MPU, mobile PU. So three processors put together, the most important issue is the computer machine architecture. We have a three computer machine and how to integrate together and increase the performance. And you say it's 500 times more. Yeah. And I agree, if you combine the three PU together, it's going to be 1,000. And the most issue, the challenge is the we call open computing machine architecture. How to put together increase performance, especially for the mobile devices, because we cannot consume the power, the batteries issue. So what do you think about for the mobile device size there? How to make sure the 500 or 1,000 times more as much as possible? That's a very difficult issue.
I think mobile computing will take this idea of co-processing to the nth degree. For example, Tegra has more than 2 processors. Tegra has 8 processors inside. And the reason for that is because you know what you're doing when you're on a mobile environment. You know, this notion of multitasking and so on and so forth is a little bit more limited when you have a device this big. So you're either talking on the phone, or you're watching video, or you're doing video conferencing. Whatever you're doing, there's a use case. And you should design, and because silicon's free, transistors are free, you could design the right processor combination for that use case, and as a result, consume almost no power. And so my guess is that for mobile computing, we're going to go further into this direction of co-processing or a lot of processors. Yes, sir.
Jose Renau, UC Santa Cruz. The GPUs tend to have a bigger power envelope, not the CPUs. Do you see this gap for the high performance part, not the mobile? widening, so the GPUs keep increasing the power consumption while the CPUs get under 100 watts, so the GPUs are going to go down? What's your intuition there?
We put an enormous amount of energy into this idea called perf per watt. And ultimately, it's not so much the power of the processor, but the power efficiency of the processor. If the architecture is good from a perf per watt perspective, and we're always taking improvements there, every single generation we try to find a way to improve our perf per watt. When we improve our perf per watt, you apply that architecture across the board. Some customers want to have a 300-watt GPU because their environment affords it, and that's the way that they would like to buy their product. And some people would like to have more GPUs, each one of them being 20 watts or 10 watts. And so the important thing is not so much the choice that we made in the design of the product, but the architecture that we design to enable all these different products have to be the best in perf per watt. And so if you were to compare the perf per watt of a homogeneous computing architecture versus that of a heterogeneous computing architecture, it's incomparable. I mean, you're probably, the heterogeneous architecture is likely in performing these applications, 50 to 1 better in perf per watt. And so it's really incomparable. Okay? I want to thank all of you for coming today, and have a good conference.